Hello everyone. We today discuss remaining next part of that surface chemistry, that is catalysis. What is catalyst support? We know that for increasing the activity of catalyst used must be in a powdered form, and therefore in many reactions, if reactants are in gaseous and liquid states, then that powdered catalyst is coated on neutral support material like inner wall of pipes made up from that neutral material. That materials act as a support. Then that supporters used commonly used supporters are charcoal, alumina, asbestos, Kazelgar, silica gel, silica alumina, such then salts like calcium carbonium, magnesium sulfate, and barium sulfate. Such materials are used as supports. Then the method for applying that coating of that catalyst, that is similar to coating of color coating inside wall of that pipe like neutral support. Then what are promoters, inhibitors, and catalytic poisoning? Promoters first. The minute quantities of substances required to improve the activity of catalyst, to improve the substances used to increase the activity of catalyst, to improve the activity of catalyst, that are known as promoters. Then inhibitors. The minute quantities of substances which decreases the activity of catalyst, that are known as inhibitors. Then catalytic poisoning. Certain substances reduces the activity of catalyst, that are known as catalytic poisoning. That poison substances react chemically with catalyst and block the surface area of catalyst, or they may adsorb on the surface of catalyst and block the surface of catalyst. Therefore, catalyst surface not available for reaction. That catalytic poisoning is of two types. Temporary poisoning, which can be removed by removing that substances and restores the original activity of catalyst, that is temporary poisoning. Permanent or true poisoning, catalyst is permanently deactivated and cannot be regenerated again. This is about that catalytic poisoning. Then mechanism and kinetics of catalyzed reactions. Mechanism and kinetics of catalyzed reactions. For Illustration of this mechanism and kinetics of catalyzed reactions, we consider first general reaction, that is R plus C reversibly gives X as intermediate. That forward reaction rate constant is K1, and for this backward reaction rate constant is K2. That is X generated by combining reactant, that is R and C, while X again decomposes into R and generates R and C. Rate of decomposition is X K2 and rate of generation of X is K1. Then that X is unstable intermediate, which converted into product, that is X converted into P plus C. Rate of this forward reaction is, rate constant is K3. Reversible reaction considered. That second step may be considered irreversible. That is first step only if reversible. That second step also reversible. Both steps here, generation of catalyst is also reversible, and that second step, that intermediate intermediate generation is also reversible, first step, and that intermediate converted into product, second step, is also reversible. Then we can write here rate of formation of product, per unit time, that is rate of reaction, that is nothing but rate of reaction. How will you write that? dP by dt is equal to, that dP by dt is equal to, if that rate constant is already known, that then that dP, that is product, is here, dP by dt is equal to K3 into RH. RH is intermediate here, X, K3 into X. That is, that rate of product formation depends on concentration of intermediate. Concentration of intermediate here, RH. Concentration of intermediate. dP by dt, we can write here dP by dt, that is rate of formation of product per unit time, is proportional to X, that is concentration of intermediate. Therefore, dP by dt is equal to K3 into concentration of X, K3 into concentration of X. Then that the concentration of intermediate X can be found out by using steady state approximation. Steady state approximation. What is steady state approximation? That is, during the reaction, such reaction, there is a one time where concentration of this X, intermediate X, in reaction medium becomes constant. That is, rate of formation of X, rate of formation of X, rate of formation of X. What is rate of formation of X? K1 into R into C, concentration of R into concentration of C. K1 into concentration of R into concentration of C. This is rate of formation of X is equal to, what is steady state approximation? Rate that is that concentration of X in reaction medium remains constant is a steady state approximation. Why constant? Because the rate of formation of X is equal to rate of degradation of X, rate of degradation of X. How that X formed? X formed by forward reaction. In this case, R plus C, it gives X, rate constant is K1. How that one is decomposes? That decomposes by two ways. That is second step, that converted into product P plus C, and that may be again converted back to R plus C, R plus C. Therefore, we can write here as a rate of degradation of, rate of formation of X is equal to rate of removal of X or degradation of X. That is, formation is one way only, that is K1 into concentration of R into concentration of C. But here removal of X, that is by two ways, that K2 into concentration of X, K2 into concentration of X, that is, and K2 into concentration of X, and another way K3 into concentration of X. That means here K2 into concentration of X, that means backward reaction, first step, backward reaction. K2 into concentration of X, that is first removal, that is X again generates R and C. X again converted into R and C. What is rate of that backward reaction? K2 into concentration of X, K2 into concentration of reactant, that is X here for backward reaction. Then another way of removal of X is K3 into concentration of X, that is product generation, that is K3 into concentration of X. Then thus here rate of formation of X is equal to rate of removal of X. X removal of X is by two ways, while formation of X is by one way only. Then by rearranging, we got the value of X, concentration of X, concentration of intermediate X is K1 upon K2 plus K3 into concentration of R into concentration of C. Then substituting value of X in the equation, that is rate of product formation equation, that is, what is that rate product formation equation? dP by dt. dP by dt is equal to, dP by dt is equal to, that concentration is proportional to concentration of rate constant into concentration of X, concentration of X. Then concentration of X is here, value of, that is K1 upon K2 plus K3 into concentration of R into concentration of C. This one is concentration of X. Then rate of product formation will become Kc into, K1 into K3 upon K2 plus K3. That K3 is initial. That rate of product formation equation we can write here as a rate of product formation in second step. What is that equation? dP by dt, dP by dt, that is rate of product formation. Product is here P, rate of product formation. dP by dt is equal to K3 into concentration of X, K3 into concentration of X. Value of concentration of X is here. In equation 3, we got value of concentration of X. Substitute that dP in by dt equation. We got K3 is as it is. Therefore, K1 upon K1 into K3 upon K2 plus K3 into concentration of R into concentration of C. Then dP by dt is equal to Kc, which is new constant, Kc into concentration of R into concentration of C. Then therefore, the rate of product formation, that is rate of reaction, depends on concentration of catalyst also. C is here catalyst. Therefore, product formation depends on concentration of reactant as well as concentration of catalyst, that is C. And here new constant Kc, which is equal to K1 into K3 upon K2 plus K3, is known as catalytic coefficient. Then this one is we discuss that mechanism for catalytic reaction by considering general reaction. Now, by same way, we discuss this by mechanism for acid catalyzed reactions. After this, we discuss same way apply same criteria for base catalyzed reactions and enzyme catalyzed reactions. We consider here first acid catalyzed reaction, that is reactant R plus catalyst acid, that is HA, reversibly gives intermediate RH plus plus A minus. Then that intermediate RH plus in the next step converted into product by reacting with water. Concentration of water is excess. Therefore, that RH in next step converted into product. Therefore, here by applying steady state approximation, here intermediate instead of X, intermediate is RH. Therefore, rate of formation of intermediate is equal to rate of removal of intermediate. Same way here we write for this reaction, that is K1 into concentration of R into concentration of catalyst HA is equal to K2 into concentration of A plus K3 into concentration of RH. Then by rearranging, we got concentration of RH is equal to K1 into concentration of R into concentration of HA upon K2 into concentration of A minus plus K3. Then here concentration of H2O is excess, therefore not necessary to consider. Then substituting this concentration of intermediate in equation for product rate of reaction equation, that is dP by dt is equal to K3 into concentration of RH. This equation, by substituting that value of concentration of intermediate RH, this equation become dP by dt is equal to K1 into K3 into concentration of R into concentration of HA upon K2 into A minus plus K3. Then this is equation for rate of reaction. Consider here there may be two possibilities. First possibility, that value of K3 is very greater than value of K2. That is, what is first case? In this case, if we consider this reaction, that RH, decomposition of RH, removal of RH is of two types, two ways. Here case 1 is considered that RH again converted into reactant R plus HA, and second way RH react with water and converted into P. Rate of this P formation is very larger than rate of decomposition of RH back into R plus HA. This second way is very greater than that of this backward again generation of R plus HA. This R plus HA generation again from RH is considered very less, and this second way product formation rate is very high. This is first case we consider. There are two possibilities out of that possibility. This possibility is we consider. What is next possibility? Second possibility, that RH again generate R plus HA backward reaction, that is K2. Value of K2 is very larger than K3. That means rate of generation of product is less. This one is second possibility. Consider these two possibilities. First we consider first floor possibility, that is K3 is very larger than K2. Then neglecting that K2 into A, we got dP by dt is equal to K1 into R, concentration of R into concentration of HA. K1 into concentration of R into concentration of HA. That means rate of reaction, product formation, rate of product formation dP by dt depends on concentration of reactant as well as concentration of catalyst. Catalyst concentration also important for this rate, for the rate of reaction. That also depend on R as well as HA. This is first approximation or consideration. Then pH effect on this reaction, effect of pH. Consider rate of product formation equation, dP by dt is equal to K into R into HA. For acid catalyzed reaction, rate equation is dP by dt, that is rate of product formation per unit time, is equal to rate constant K into concentration of R reactant into concentration of HA, that is acid. For acid catalyzed reactions, the concentration of acid remains constant. Therefore, rate equation K is equal to KH into concentration of H plus, that is acid. Taking logs, log of K is equal to log of KH plus log of H plus. But minus log of H plus is pH, therefore this equation become log of K is equal to log of KH plus minus pH. Then if a plot of log of K, log of rate constant K versus pH, if we plotted, it will be straight line with negative slope. That indicate that rate of acid catalyzed reaction decreases with increase in pH, because reaction is acid catalyzed. As pH increases, concentration of acid decreases, and therefore as concentration of acid decreases, rate of reaction also decreases. This next thing is base catalyzed reactions that are same here. Consider same as a acid catalyzed reaction. Consider that equilibrium reaction of base B and reactant RH. RH plus B reversible with BH plus R minus, forward K1, backward K2, rate constant. Then second step, rate of product formation, it is R minus, which is base here, react with water gives P product plus OH minus. Then apply that steady state approximation. Then for this directly all apply steady state approximation, then find out the concentration of value of equation for concentration of BH, then by substituting concentration of BH in rate of reaction equation, rate of product formation equation, then all that procedure, by applying all things, we here got equation, that is K is equal to, for base catalyzed reactions. For acid catalyzed reaction, what was the equation? That one is for acid catalyzed reactions, we here turn K is equal to H plus KH plus, that is rate constant for that acid catalyzed reactions, is into concentration of H plus. Same way here for base catalyzed reaction, we write here that K into rate of that base catalyzed reaction is equal to rate constant for base catalyzed reaction, that is KOH minus into concentration of OH minus. That is then taking logs, but here since Kw is equal to ionic product of water, Kw, concentration of H into concentration of OH, therefore concentration of OH is equal to Kw upon concentration of H, therefore K, which is equal to, substitute in a previous equation, substituting value of that concentration of OH minus, that equation become K is equal to KOH minus into Kw upon concentration of H plus. Taking logs, log of K is equal to log of KOH plus log of Kw minus log of H plus, which is nothing but pH. Therefore, log of K is equal to log of KOH plus log of Kw plus pH. Therefore, log of K is equal to log of KOH minus pKw plus pH. If we plot graph of log of K versus pH as like previous graph, then we obtain straight line with positive slope. That indicate that For base catalyzed reactions, rate of reaction increases with increase in pH. Then consider enzyme catalyst reaction, same way here. Then apply steady state approximation, same way here. Yeah, then by applying steady state approximation, find out value of ES intermediate, concentration of intermediate. Then this one is value of that equation for concentration of ES. Then substitute that equation value of ES, concentration of ES, in rate of product formation equation or reaction rate equation. Then therefore rate of reaction is K2 into concentration of ES. Substitute that above concentration of ES in this equation. Therefore rate of reaction is equal to, this one is K1 into K2 into concentration of enzyme E0 plus S upon K1 into concentration of S plus K2 plus K3. Then by substituting, rearranging, dividing by K1, we got equation as a rate, final equation, that is K2 into E0 in concentration of enzyme E, which is plus concentration of S upon Km into S. Then there are two cases. First is when concentration of substrate S is very small, then that rate become concentration of S, hence reaction is first order. Second case is when concentration of S is very larger than Km, then equation becomes rate is equal to K2 into concentration of E0, that is rate is proportional to concentration of E0. As rate is independent on substrate, hence concentration of substrate concentration, hence reaction is zero order. Here rate depends only on enzyme concentration. That means reactants that substrate concentration not affects on rate. That means reaction is zero order. And in this case, reaction is depend on substrate concentration. Therefore, reaction is first order. This is about that enzyme catalyzed reaction. Then heterogeneous catalysis, that reactants, catalyst and product are in different physical states. Reactants are gaseous or liquids and catalyst is powdered solid. Then reactant molecules get adsorbed on the surface of catalyst and react to form product molecules, which are then deadsorbed and deadsorbed from the surface of catalyst. And that adsorption that are of two types, that is physical adsorption and chemical adsorption. Physical adsorption, the reactant molecules are adsorbed on the surface of catalyst by weak physical forces called van der Waals forces of attraction. For example, adsorption of inert gases on activated charcoal. Then chemiabsorption, reactant molecules are held on the surface of catalyst by strong chemical forces called valence forces. For example, sulfur dioxide react with oxygen gas, both are gases, that gives formation of sulfur trioxide. two molecules. This reaction is reversible, very difficult, and takes place on surface of catalyst like platinum or vanadium pentoxide. This is a reversible, very difficult step in the contact process. And when gaseous reaction takes place on a surface of solid catalyst, four steps are involved. First, diffusion of gas molecules on catalyst surface. Then second, adsorption of gas molecules on catalyst surface. Third, chemical reaction takes place among that catalyst on that catalyst surface among that reactant molecules. And fourth, deadsorption of product molecules on this surface. That means catalyst provide surface for that reactant molecules to combine together. That reactant molecules first adsorbed on the surface of catalyst, and then they combine together on the surface of catalyst. And when they combine, product formation takes place on the surface of catalyst, and once product formation takes place, they deadsorbed from the surface of catalyst. Then surface of catalyst become free for new molecules, new reactant molecules. This is about that catalysis part of this surface chemistry. Here is the end of this topic. Okay, thanking you.